believing that yourself. All right, let's get launched here. This computer went to sleep on me. I said, well, I had it plugged in. It should have been working. But one of those little leaves got caught in the blade for the plug, and so it wasn't making a connection. It's like, oh, we got to get this fixed right away because I can't be having this battery go dead on me. Let's launch this and see what we've got. Okay. So I don't know what you all may have read out here or heard from other people about what we're going to be doing this morning, but so several weeks ago, got this message from Diana. She said, can you come back to Wickenburg and give a talk? And I said, sure. Would you like me to give a regular old sermon, or do you want me to give a creation talk? And she goes, oh, well, give us a pair of creation talks. Okay, I can do that. I said, I just so happened to have recently finished a talk, which I'd be happy to try out here. And then one of my speakers in Payson, a guest speaker who was going to be coming up, was going to be talking about rock formations. And he said, oh, I got the date wrong on this. It's not going to work. And I said, don't worry about it. I got one. I'll practice it here instead of at Wickenburg. And it's a good thing I did because it wound up going an hour and 20 minutes. And so I've gone through and I says, well, I thought I had pretty much stuck with the essentials, but I was able to trim a few more things off. So if we start now, we should be, we'll be able to take care of that appetite that comes up at lunchtime. So I named this talk, God of Wonders, God of Numbers. Mathematical laws and properties confirm the biblical account of creation by displaying three things: order, complexity, and beauty in creation. So we're going to look at these things today, this morning. And I'm trusting that you will come away with an even more assurance that God's Word is true. We're going to have a little bit of audio later, so I want to run this little audio-video check here. So if you have one of these things, you don't want to be embarrassed by having it go off on you later, so you can take care of that. All right, so I have a scripture verse I'm going to start off with. Proverbs 25:2. It is the glory of God to conceal a matter, but the glory of kings is to search out a matter. Now, none of us here, I don't believe, have made any claims to nobility, so we're not going to say kings in that respect, but the verse implies that it's a noble thing to do to search out a matter. And so what we're going to do is we're going to look at some things that are going to involve a little bit of investigation. Fortunately, the investigation was done by some other people, and we're going to reap the benefits of their investigation. So I'm going to take you today, which will lead us to taking a little peek into the mind of God. Now, that might seem like a pretty bold claim, and well, in some respects it is, but I think it'll be a little less mysterious to you as we get along. So really quickly, I want to tell you that the inspiration for this talk came from a variety of sources. Primarily, it was going to be a presentation that I witnessed in Oregon at an organization called DSA, and this is not going to show very well on the screen, so forget the laser pointer. The DSA stands for Design Science Association, and it's an organization that I was associated with in Portland, Oregon before we moved here. And a man by the name of Brandon Church gave this talk on the solar system, chance or design. And he went through and he showed all these example after example after example after example after example of design in the solar system, mathematical design in the solar system. And that was really inspiring. And I kind of, in the back of my mind for all these years, been thinking, one of these days I'm going to take that, I'm going to do something with it. And that was the initial inspiration. But then there's also this right here, this gentleman, Spike Passaris. He has an organization, and he does his own ministry. It's called creationastronomy.com. I've had him as a guest speaker in Payson before as well. He went to work for NASA years ago as an engineer in their military program, and he was an atheist and an evolutionist. But because of the data that he was working with, he said, this can't be coincidental, this can't be randomness, and it eventually led him to become a creationist, which then led him to say, well, now who's the creator? And that led him to becoming a Christian. And so he talks a little bit about that, but he has 3 different videos which are highly recommended, and the title is interesting. He says, What You Aren't Being Taught About Astronomy, Volume 1, 2, and 3. And he takes you through, the first one's about the solar system, the second one is about stars and galaxies, and the third one is about the universe. And it is available on his website, creationastronomy.com, but it is also available at these other following websites: ICR, which is Institute for Creation Research, Amazon.com, ChristianBook.com, AnswersInGenesis.com, and I also found it at RainbowResource.com and CreationSuperstore.com. So you can find this a lot of places, but if you typed his name, Spike Psaris, or What You Aren't Being Told About Astronomy. Then there was another video series that was produced recently called The Heavens Declare, and it's produced in three-part series. There's actually now another set of 3, and The Heavens Declare is produced by Awesome Science Media, and they're based out of the Northwest, and they have really good resources as well. So if you were to go to Awesome Science, or AwesomeScienceShop.com is the name of their store, they have a lot of very good materials that I would highly recommend. The next resource also is this video produced by Illustra Media called The Privileged Planet. And it talks all about Earth, and Earth being a special planet in the place in all of creation. And the last one here I'm going to talk about, next to the last, this next one is called The Case for a Creator, featuring Lee Strobel. It's available on Amazon, eBay, ChristianBooks.com, Walmart, and a few other places. And Lee Strobel, again, he was an atheist, and his wife challenged him because he's an investigator. He's a legal journalist. He was the legal editor for the Chicago Tribune newspaper. His wife one day challenged him to use his journalistic investigating skills to investigate the claims of Christianity, and he did, and it took him 5 years, but eventually he realized this makes more sense than everything I'd been taught, so he is an advocate for creation. And then, lastly, we've got this video here produced by Institute for Creation Research, The Secret Code of Creation. This is where we're going to be ending up near the end of the talk. And it's available through the Institute for Creation Research website, icr.org. Okay. I'm going to start you off here with a little biblical mathematical riddle, okay? Did you know that such a thing exists? Maybe not, but here we go. So here is your riddle. Remember how Samson proposed a riddle? Okay, well, I'm going to propose a riddle to y'all. 500 begins me, 500 ends me, a 5 in the middle is seen. The first of all letters, the first of all numbers, fills in the spaces between. Who am I? And in your mind, you can be thinking about the Jeopardy theme song, the final Jeopardy theme song. So, 500 begins me, 500 ends me, 5 in the middle is seen. First of all letters, first of all numbers, fills in the spaces between. Does anybody want to venture a guess? The answer to this riddle? The answer is King David. You say, how is that? D is the Roman numeral for 500. 500 begins me, 500 ends me, 5 in the middle is seen. First of all letters, first of all numbers, fills in the spaces between. Okay. This presentation this morning will explore mathematical sets, mathematical properties. We're going to look at something called fractals, which will take us to learning about Fibonacci numbers, and many of us have heard about Fibonacci numbers for a little while, which will take us to the golden ratio. Then we'll look at those aspects of our solar system, and then we're going to conclude with examining something called the Mandelbrot set. Is anybody here familiar with the Mandelbrot set? Only a few. Well, that's good. Okay. All right. So first of all, we're going to ask the question, what is mathematics? Now, a lot of people think, oh, math, that's like, arithmetic, right? Well, actually, no, it's more than that. Mathematics, if you go to Merriam-Webster's dictionary, it will tell you that mathematics is the science of numbers and their operations. So mathematics involves everything. In fact, it involves algebra, arithmetic, calculus, geometry, trigonometry. So anything that involves mathematics, computation, numbers, that all is under the umbrella of mathematics, if you will. So what are numbers? Well, numbers are basically a concept of quantity, and they are abstract in nature. So numbers are a concept. So we need to grasp that right away. So we think of numbers, a lot of us have been taught mathematics for a long time. So we think, well, okay, numbers. We are so familiar with them that we take them for granted sometimes. So I'm going to put this up on the screen, and I'm going to ask you, what is this? Does anybody want to venture a guess? Okay, now if you said it was the number 3, you would be wrong. It's actually the numeral 3. We use numerals in place of the numbers. The number itself is abstract. This is not the number 3, because if this were the number 3, then I just made 3 go away, and now you're going to have to count 1, 2, 4, 5, 6, 7, like that. Okay, so numbers are abstract. Okay, they don't exist in the material world, but yet we all understand numbers, and we all understand number concept, and we all understand counting and adding and subtracting, especially when you get your first checking account or credit card or something like that. So now there's some points that we need to keep in mind. Laws of mathematics are conceptual. It is a concept. It is an idea. And we use it all the time. We're so familiar with it that we don't even give much thought about it. So today I'm going to try to bring your attention closer to how numbers fit into this whole realm of creation. Numbers exist in the mind, okay? You can't touch them, you can't taste them, you can't feel them, you can't go to any museum and see one on display. The laws of mathematics existed before there were people. So whether you're a creationist or an evolutionist, okay, the properties of mathematics and numbers existed before there was a human being walking on the earth. They are therefore not the product of a human mind. So where do they come from? Well, numbers originated in the mind of God. Okay, for God to be able to speak creation into existence, he had to have an idea of what he wanted when he spoke, and that would have involved mathematical properties. So this is a little representation of Johannes Kepler. He lived from 1571 to 1630. Kepler is most famous for discovering the laws of planetary motion. Now, I say discover because Kepler did not invent the laws of planetary motion. He only discovered them by making observations and seeing how they worked, and he was able to give us the laws of planetary motion. We're going to look at those. We're not going to really look at those, but we're going to look at some of the planets. But Kepler is more famous for having made the statement that he was thinking God's thoughts after him. In fact, this is the entire quote. It comes up this way. He says, "I was merely thinking God's thoughts after him. Since we astronomers are priests of the highest God in regard to the book of nature, it benefits us to be thoughtful not of the glory of our minds, but rather above all else, the glory of God." So the glory of God is why we're here today, and it's what we're going to be learning about as we go through this talk. So we're going to start off by reviewing the nature of numerical sets. So I'm going back to the Encyclopedia Britannica in this case. Set is, in mathematics and logic, any collection of objects or elements which may be mathematical, numbers, or not. Okay, so a set is a collection of something, okay? When I was little, I had a set of Matchbox cars, okay? And other people have sets of stamps or pennies or whatever they want to collect. So a set is a collection of elements with a common defined property. Okay, if you have a set of glass insulators from old telegraph lines or telephone lines or whatever, you get the idea. Okay, so we have sets of things. Some people have sets of china or whatever. In most sets, speaking of numerical sets, some numbers are included and others are excluded. Okay, so and we've all talked about sets. So we're just going to do a little mathematical review here. If I put this up and I said, I want to create a set of even numbers. You would look at these numbers and you'd say, okay, yeah, we can put some in a set of even numbers. So let's do that. Let's move 1 out of the way. And let's put 10 up there. And let's move 6 over there. And let's scoot 24 over. And we'll slide 12 up there. And we'll get 7 out of the way. And we'll put 144,000 up there. And that comprises our set of even numbers. So everything within our little blue box is part of the set of even numbers. Now, it's not a comprehensive set. These aren't all the even numbers, but out of the numbers that were available, these belong to the set of even numbers. So everything else outside here is not a part of the set of even numbers. Now, if I said, let's create the set of negative numbers, well, you say, oh, I can spot those easily. They're the ones with the little thing in front of them, right? Okay, so let's get 24 out of the way, and we'll put 1 way over there on the right. And as you know, negative numbers decrease in value as you go that direction. And so now we've created a set of negative numbers. Okay, so now I want to say, let's look at prime numbers. Now this is going to tax you just a tiny bit more. You have to say, oh, prime numbers, yeah, those are the ones that can only be divided by 1 in itself. Okay, so let's see how that works there. 1 by definition is not a prime number, so we'll start with 3 and 5 and 7 and 17. Okay, sets of prime numbers. So now we know these things are in the set of prime numbers and everything else is not. So now we're just going to jump ahead quickly and preview the set of Mandelbrot numbers. What are Mandelbrot numbers? They are the set of numbers, C, for which z to the nth power remains small according to this formula. Zn squared plus c equals Zn plus 1. And you look at that and you're going to say, well, you just lost me. Okay, that's all right. We're going to go back and we're going to explain this later. I just want to introduce this now to give you a heads up of what's to come. So we're going to be looking at numbers that belong to this set. But I have to make a statement at this point. Proponents of evolution have to believe that matter, energy, space, and time are all that exist. There is no organizing force in the universe. Everything simply came to be randomly. Okay? Keep that in mind. In fact, they even say in evolutionary literature that they have to remind themselves that what looks like order and complexity and design is just an appearance of order, complexity, design. It actually all came about by random processes. In fact, Richard Dawkins, one of the leading foremost atheists running around the planet today, this is his little thing there. He said at one time, biology is the study of complicated things that give the appearance of having been designed for a purpose. He said that in his book, The Blind Watchmaker, which he published in 1986. Now, we're not going to be talking about biology today, but this is an important point. He says that there are complicated things that people observe that have the appearance of having been designed for a purpose. What I'm going to reiterate to you today, and many other people in other fields say the same thing, is that when you see evidence of design, you can assume that there was a designer. You don't have to say, well, yeah, it looks like design, but I'm supposed to believe something different. All right, that being said, if evolution is true, and if everything came about by random chance happenings, where did numbers come from? How did numbers originate? Because we said, we're going to do a question and answer a little bit later, okay? But hang on to your question. Where did numbers originate from? Okay, now we said that numbers are abstract, okay? They're conceptual. So they're not material. So they don't exist in nature, but evolutionists say that everything that came about just came about by random process. Did the number 3 evolve into the number 7? Okay. Or has 3 always been 3, and has 7 always been 7? All right. So we made the point that numbers are non-material. They are abstract. They're not made of matter. They don't reside in physical space. Numbers don't reside in physical space means, again, there's no place that you can go to say, oh, this is an example of number 3. The metric system. You know, there are the displays where they have this is a meter, and this is a, this is a liter, and this is a gram, and everything else, and we have set standards, weights, and measures that we can say this is the model that we base everything else off of. But numbers don't have that. Third thing, numbers have always been the same. They haven't changed, they haven't evolved. And is there anybody that you can think of on the planet that denies the reality of numbers? Well, no, everybody accepts that numbers exist, okay? And numbers have these 3 attributes. They are non-material, they don't reside in physical space, and they have always been the same.
Excuse me?
Yes?
But their appearance has changed over time. Their value is always the same, but their appearance has changed. Like from a chip in hieroglyphic numbers to something for Latin, then English.
Well, that's where we're talking about numerals and numbers. The concept of numbers stay the same, but the expression of numerals, because we have Roman numerals, we have Arabic numerals, and we have other sorts of numerals. So how we write them or how we express them can change based upon the culture and the language. But the concept of number 3 is still 3, and 7 is still 7. So let me point this out then, using those 3 thoughts. God is non-material. He is a spirit. In John 4, verse 24, Jesus says, God is a spirit, and those who worship him must worship him in spirit and in truth. Secondly, God doesn't reside in physical space. 1 Kings 8:27. But will God indeed dwell on the earth? Behold, heavens and the highest heaven cannot contain thee. How much less this house that I, Solomon, have built? And the third aspect, God has always been the same. Malachi 3:6 tells us, for I am the Lord, I change not. In other words, numbers and God share common attributes. Mathematics is one abstract expression of the characteristics of God, because they, like God, are non-material, they don't reside in physical space, and they have always been the same. 3 has always been 3. And yet, while there are people who don't deny the reality of numbers, they will try to deny the reality of God. Isn't that somewhat interesting?
That's just stupid.
Well, you stay with me. You watch the rest of the program. Numbers existed in the mind of God before the world was created and before there was a living man to discover them. Now, there are 4 basic properties of mathematics. Now, there are a lot more than 4, but we all, as we went to school, we learned 4 basic properties of mathematics, and they would be the commutative property, the associative property, the distributive property, and the other one was called the identity property. Now, I'll just do a quick review of all these because, again, we're talking about properties. Commutative property is where you can 3 plus 5 equals the same as 5 plus 3, which equals the same as 8, so on. Associative property, you can group them differently if you're adding them up. And these work for addition and multiplication, not for subtraction or division. The distributive property is where you can break something out and make it a little more spatial, and it still comes out the same way. And then we have the identity property. If you're adding with 0, you get the same. If you're multiplying by 1, you get the same. Okay. Man did not invent these mathematical properties. He only discovered them. Okay, there was nobody that says, I'm going to create a property about math that says this. No. What they did was they discovered this trait, and then they gave it a name, and then they made a definition for it. But the mathematical properties would all have been true before the Garden of Eden. Colossians 1:16 tells us this, for all things in heaven and earth were created by him. All things, whether visible or invisible, whether thrones or dominions, whether principalities or powers, all things were created through him and for him. And I propose to you today that all things includes numbers, even conceptual and abstract things. God invented numbers, which means that God invented mathematics, which means that mathematics is an expression from God which can be used to glorify him. And one way he does that is by giving us fractals. Fractals, definition, any of various extremely irregular curves or shapes for which any suitably chosen part is similar in shape to a given larger or smaller part when magnified or reduced to the same size. What did he just say? I'm going to give you some examples. It'll clarify all that. Simply put, a fractal is a pattern, either naturally occurring or abstract, and it repeats itself. Now, if it occurs in nature, at some point it will terminate. Abstract ones may or may not terminate. So some examples of fractals in nature would be pine cones. These are fractal in nature. Another example would be cactuses or cacti. Some of them spin in a clockwise direction, but there are certain types of cactus that spin in a counterclockwise direction. And some of them, you look at it, it's kind of hard to tell which direction they're spinning. Frost on a window pane freezes in fractal patterns. There is even something called Romanesco broccoli, which is a fractal pattern. Lightning bolts coming down out of the sky come down in a fractal pattern. And a lot of us have seen ferns before. Ferns exhibit a fractal pattern. Now, this fern is a naturally occurring fractal pattern. This next one I'm going to show you is an abstract form, but I want you to see how this works. Okay, notice that the stem of the plant starts off at almost vertical and curves this way. We're going to start magnifying in on this fractal pattern here. And as we continue to zoom in, we see the same thing being repeated again and again and again. Now watch, coming up, this frond right here is where we started. And now we're repeating the whole cycle again and again. So this is an example of an infinitely repeating fractal because this is abstract in nature. But it is a representation of the actual ferns that exist in nature. And this is called a Barnsley fern, by the way, in case you want the name for that. So that brings us to this man who we know by the name of Fibonacci. Now, we actually owe quite a bit to this guy, more than you might think. And I'm not saying that because I'm half Italian and he's all Italian. But Fibonacci, whose actual name was Leonardo Pisano Bagoio, Fibonacci was his nickname, first introduced this series of numbers known as the Fibonacci sequence in his book Liber Abbasi, the Book of Calculations, which he wrote in 1202. This goes back a few years, right? Fibonacci was a member of an important Italian trading family in the 12th and 13th century. Being part of a trading family, mathematics was an integral part of his business. Fibonacci traveled throughout the Middle East and India, was captivated by the mathematical ideas from his travels. His book, Liber Abbasi, was a discourse on the mathematical methods in commerce that Fibonacci observed during his travels. Fibonacci is remembered for two important contributions to Western mathematics. He helped spread the use of Hindu systems of writing numbers in Europe, 0, 1, 2, 3, 4, 5, in place of Roman numerals. So it's thanks to Mr. Fibonacci, we don't have to use those cumbersome Roman numerals. We're able to use this system. And then he invented what was the seemingly insignificant series of numbers, later named the Fibonacci sequence after him. Now, it seemed insignificant at the time until more work was done on it, and as more people began to really delve into Fibonacci and his numbers and his number sequence, they began to see things that began to say, this is more than being insignificant. Now, here is part of the reason it seemed insignificant. He discovered this sequence of numbers by posing the following question. If a pair of rabbits is placed in an enclosed area, how many rabbits will be born there if we assume that every month a pair of rabbits produces another pair and that the rabbits begin to bear young 2 months after their birth? Now, leave it to somebody who is an Italian with too much time on his hands to be thinking about rabbits and how much they would breed and how many they would go by. But aside from that, okay, so here's how this plays out. So at the start, you have no rabbits are born as the initial pair has not had time to get pregnant and be born. The first month, one pair of rabbits are born. The second month, again, only one pair of rabbits are born as the new rabbits have not yet matured so that they can bear young. The third month, you have 2 pairs of rabbits reproducing, and 1 pair is not ready, so you have 2 pairs of rabbits are born, so the number goes to 2. In the fourth month, you have 3 pairs of rabbits that are now reproducing, and 2 that are not ready, so the 3 pairs of rabbits are born, and you get the number 3. The fifth month, 5 pairs of rabbits produce, and 3 are not ready, so 5 pairs of rabbits are born, and so on. So that leads us to, if you follow this line of mathematics out, you are left with a sequence of numbers called the Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, and so on. Now, let's look at what happens when you divide the resultant number by the number that precedes it, okay? So if we take 1 divided by 1, we get 1. We take 2 divided by 1, we get 2. 3 divided by 2, we get 1.5. 5 divided by 3, we get 1.6. 8 divided by 5, we get 1.6. 13 divided by 8, we get 1.625. 21 divided by 13, we get 1.61, etc. 34 divided by 21, we get this number. 55 divided by 34, we get this number. 89 divided by 55, we get this number. Are you beginning to see a pattern developing here? 144 divided by 89, we get this number. 233 divided by 144, we get this number. 377 divided by 233, we get this number.
And all the numbers begin with 1.61.
Yep. Now, the number of iterations. If we can, there's several ways that we can compute Fibonacci numbers. You can do it by fractions or you can do it by square root. And then here is what we get. And you begin to see that at some points, these numbers are all very, very closely aligned. But the 1.618 is pretty good. So this number now then was given a label, a name, the golden ratio. And you can compute this way. And this is Greek letter phi, which is, again, the laser doesn't work on the screen here, equals 1 plus the square root of 5 divided by the number 2. So let's see how that works. I'm sorry?
Also known as 45 degrees.
So if we take, now here's another way of expressing it. X squared minus x minus 1 equals 0 when x equals this number. So let's take this number. The square root of 5 is 2.2360679. If we add 1 to that, we get 3.2360609. If we divide that by 2, look what we get, 1.6180339. This golden ratio is also expressed geometrically in a linear fashion by looking at this. So if we take the length of the entire line, AB, the entire length, A plus B in purple, is equivalent to the line segment A by the same ratio that A is to the smaller line segment B. So you get this? The relationship of the big one to A is the same as the relationship of A to B, just on a slightly smaller scale. It works the same way with two-dimensional objects, golden rectangles. If you have a square, AA, and you make a rectangle, AB, the entire width of this rectangle, the relationship of that to A is the same as A to B, or the same as the volume of the square. And that was given this Greek letter phi as an example. And this ratio comes out to be 1.61. Well, interestingly enough, it also shows up in pentagons and pentagrams. So it says line segment DE, the ratio of line segment DE to line segment EX. So let's look at that. DE to EX. DE to EX is the same as the segment EX is to XY, which is the same as the line segment UV is to line segment XY, which is the same as the line segment EY is to EX. When I say the same, I'm talking about the same ratio, okay? And that ratio is 1.618 to 1, or, yeah. So in a pentagram, you have the same thing. Now, a lot of us have seen pentagram is the star, pentagon is the outside. So a lot of you maybe have seen this in some art before. This is called the Vitruvian Man. This is what is known in art and how the human body is alleged to fit into the same idea of the same proportions. Now, I want to take you to a little bit of pop culture here. Back in the movie 1964, there's a movie known as Goldfinger. It's introducing us to the character of James Bond in the theater, in the movies. Okay. And the main villainous character, Mr. Auric Goldfinger, makes this quote in the movie. He says, "Mr. Bond, they have a saying in Chicago, once is happenstance, twice is coincidence, the third time it's enemy action."
What's happenstance?
Happenstance means it just happened. Now, keep that thought in mind because we're going to reference this again. Once is happenstance means, hey, it happened. Twice is a coincidence, which means, well, wow, what do you know? It happened twice. The third time, you begin to suspect that there is intelligence behind what's going on. All right, quickly review the Fibonacci sequence. If you plotted the Fibonacci sequence on a graph using graph paper, you come up with something that's known as the golden spiral. How does that work? Here is how it works. We start in a small single square. We go to the next square, 1. We go to the next square, which is 2 by 2 square, and we curve it, and then we go to a 3 by 3 square, and we draw the arc, and we go to a 5 by 5 square, and draw the arc, and we go to an 8 by 8 square, continue the arc, to a 13 by 13 square, continue the arc, to a 21 by 21 square, and continue the arc, and you can see how this spiral will continue to work out. So, using the Fibonacci sequence, you can plot this spiral, which is known as the golden spiral, and you say, well, okay, so that's interesting. Well, what's interesting is when we see how this golden spiral shows up in creation. Where does it show up in creation? Glad you asked. Did you see the bulletin this morning? It shows up in rose petals. It shows up in sunflower seeds, sunflower plants, excuse me. It shows up in ocean waves. It shows up in the shells of certain creatures like the nautilus. It shows up in the coiled tails of chameleons. Remember the pine cone I showed you earlier? It shows up in pine cones. It shows up in fiddlehead ferns. If any of you like coleslaw, it shows up in red cabbage. It shows up in blue cabbage. It even shows up in regular green cabbage. It's just hard to see it, okay? It shows up in snail shells. Not only that, okay, we're talking about critters and plants and things. It shows up in weather patterns like hurricanes. And it even shows up, if that wasn't amazing enough, in spiral galaxies. The Fibonacci sequence shows itself in various places all throughout creation. Now, ponder this. Did Mr. Fibonacci invent the golden ratio, or did he discover the golden ratios? Because the galaxies were spinning before Mr. Fibonacci ever laid his eyes on one. In fact, there are websites and design companies that, graphic design companies that teach people how to use the golden ratio in designing logos and various things. In fact, many art critics have posited that Da Vinci used the golden ratio when creating the Mona Lisa to give it that type of appeal. All right, so we've talked about Fibonacci numbers, fractals, golden spirals. Now we're going to move to looking at our solar system. Now remember how I said that Dawkins said that biology is the study of complicated things that give the appearance of having been designed for a purpose? That being said, critics of creation insist that time and chance and natural selection can indeed affect the development of living systems. Therefore, if we can carefully examine a non-biological system and find order and complexity, not once, not twice, but repeatedly, that would add orders of magnitude to the confirmation that the universe was created and did not originate by random, unguided, naturalistic processes. In other words, Dawkins is saying, because biology is an active thing, you have an organism and it's interacting, it's doing different things, that you can give it the appearance of design because it has the ability to adapt and change and mutate, if you want to use that term. So we're going to look at a system that is not affected by biology. So how do evolutionists say that the universe was created? Well, talking about our solar system as it relates to us, because that's more closer to home, we know that we have these various planets here. Of these planets, how many have life on them?
One.
Only one. And most areas in our solar system are actually hostile to life. There is a branch of astronomy called exobiology. You're looking for evidence of life or the possibility of life in other places of the planet or other places of the universe, solar system, galaxy, what have you. It's like the phrase in real estate, location, location, location. Okay. Well, scientists, the astronomers, they have identified what they have come to label as the circumstellar habitable zone. In other words, you have to have the right kind of star in the first place. And our star is very unique, and I could spend quite a bit of time going to that, which, like I say, is going to be started off going to be talking about the solar system, but there's too many other good things to bring in here. But if you had the right kind of star, your planet that you have has to be in the right location relative to that star. If it is too close to the sun, like if our planet, we exist in what's known as the circumstellar habitable zone. Far enough away, but not too far away and not too close. If the Earth were only 5% closer to the sun, it would be too warm for our planet. Our atmosphere would basically boil off, and then we would be left barren and lifeless. If we were 20% farther away, we would be more like Mars, where the atmosphere would freeze, and we wouldn't be able to live, and life wouldn't adapt either. Okay, so God has placed this planet with just the right sun, at just the right distance, with just enough other features, which again could take quite a bit of time to talk about, which we won't do today. And we live in, what galaxy do we live in? The name of our galaxy is the Milky Way galaxy. Well, within the galaxy, there is something known as the galactic habitable zone. If you were to have your planet located too close to the center of the galaxy, you would be affected by radiation from other stars. You'd have other issues associated with that. Plus, you wouldn't be able to observe the heavens at all. God has placed Earth not only in the right place in our solar system, but even within our galaxy. He's put us between some of these spiral arms that happen to follow the Fibonacci golden ratio spiral. He put us between arms so that we can look edgewise on our Milky Way galaxy and see that beautiful band of light going through the night sky as well. But we can also look out and to see other parts of the galaxy to be explored. Now, God didn't have to do that, but he did it so that we can discover more about him. He wants us to explore. He wants us to discover. He wants us to see his handiwork, because that is how he has revealed himself through creation. Again, I want to mention Jay Richards, who is an analytic theologian, and Guillermo Gonzalez, who is this astrobiologist, in 2004 co-authored a book called The Privileged Planet. From that book, this video series was made, and I would really highly recommend somebody want to get that. Now, they identified in their research at least a minimum of 13 conditions that are essential for life and at the same time happen to be optimal for making observations about the universe that we live in, as if God wants his children to discover him. So what are these things? Well, here's a list. They have to be within the galactic habitable zone. You have to have an orbiting what's called a main sequence G2 dwarf star. You have to have gas giants outside in the outer solar system to protect you from incoming bombardments. You have to have a nearly circular orbit. If it was more elliptical, then the seasons, winters would be too cold, summers would be way too hot. You have to have the right atmosphere, the right mass. You have to have a moon to create tides to keep the waters from getting stagnant. You have to have a magnetic field to deflect solar radiation. You have to have plate tectonics to keep everything moving. You have to have the right ratio of liquid water to land continents. You have to have the land continents as well. You have to have the right rate of rotation. You can't be spinning too fast or too slowly. But there are also, in addition to these, a lot of these things can be expressed. You need something in the area of physics. You need certain mathematical properties in action. So these are physical traits, but there are also mathematical, physical relationships that you have to have. And here is a list of that. You need to have the speed of light has to be proper. You have to have the right gravitational force. You have to have the right electrostatic force. You have to have the right strong nuclear and weak nuclear force. You have to have something known as the Planck's constant, electron mass, proton mass, atomic mass, all these things. These are all critical as well for life to exist as we know it. And we're just going to look at one of these, and that is the law of gravitational force, or Newton's law of universal gravitation. And here's the equation. It's expressed mathematically. F1 equals F2 equals G equals M1 times M squared over R squared. And you say, again, you lost me. Okay, I'm not here to try to break this all down and explain what everything means, but I'm going to show you a little video clip from the video Case for a Creator by Lee Strobel, and it's going to talk about evidence for physics. I want you to see how finely tuned all of creation is so that life can exist on this planet here. And let's hope that we got the audio ready, and
all the matter in the universe has been governed by precisely balanced laws and constants. During an interview with Robin Collins, a philosopher with degrees in mathematics and physics, Strobel learned how these laws offer compelling evidence for a creator and conspire to make the universe habitable for life.
The laws of physics are balanced on a razor's edge for life to occur. For example, if you didn't have something like gravity that pulled matter together, you would never get planets, you wouldn't get stars, you wouldn't get any complex organisms. If you didn't have the strong nuclear force, there would be nothing to hold protons and neutrons together in the nucleus. And so you wouldn't have any atoms, so no chemistry. If you didn't have the electromagnetic force, you would have no bonding between chemicals. You'd have no light, and the list goes on. So you need all these sorts of fundamental principles have to be in place in order for life to occur. Wipe out one of those principles, wipe out one of those laws, no life.
Strobel learned that life also hinges on the precise strengths and relative values of many different physical constants. One example of this fine-tuning is the force of gravity.
Imagine a ruler divided up into 1-inch increments and then stretched across the entire universe, a distance of some 14 billion light years. For the purposes of illustration, the ruler represents the possible range for gravity. In other words, the setting for the strength of gravity could have been anywhere along the ruler, but it just happens to be situated in exactly the right place so that life is possible. Now, if you were to change the force of gravity by moving the setting just 1 inch compared to the entire width of the universe, the effect on life would be catastrophic.
no large-scale life forms could exist. Anything that was more than the size of a pea would be completely crushed. So you might be able to get life of a very, very primitive sort, such as bacteria, but you could never get conscious observers.
That's one example of the fine-tuning of the universe. And this is done and can be expressed through mathematics. Again, I refer you to this. So, getting back to this idea of how does this work in our solar system? Atheists who use the term solar system don't realize it, but they're denying their own belief system. Because if they were going to be intellectually honest, they should say solar randomness, solar chaos. When they use the word system, they're talking about a system, and systems have to be organized, and organization does not come about by randomness. But they don't call it solar chaos. They don't call it solar randomness. Systems, and again I say, if you've ever raised a teenager and looked in their bedroom sometime, you'll know that randomness does not self-organize. So, in this talk that I mentioned that took place many years ago, a math genius guy, I'm not sure what his occupation is, but his name was David Corson. He went to the NASA website and he took from there measurements of various planets in the solar system, their sizes, their mass, their diameters. And he started doing some comparisons and looking at mathematical relationships between planets in our solar system. Now, really quickly reviewing what Mr. Goldfinger says, once is happenstance, twice is a coincidence, third time is enemy action. All right, let's just take one example here. If you took the radius of the Earth, so from the center out to the edge, let's give that a value of 1. And then you make a right triangle and you make the radius of the Earth plus the radius of the Moon, okay, that's your second leg. And then you know that to get the hypotenuse of a right triangle, going back to your geometry, right, you have a squared plus b squared equals c squared. If you assign this a value of 1 and you did the mathematics, this hypotenuse of this triangle turns out to be a value of, look at this, 1.618. There's the golden ratio. There's the golden ratio again. Now, what would be the odds that that would just happen to show up that way? You say, okay, well, once is happenstance. All right, well, let's keep looking here. Let's take the diameter of the Earth, and we're going to subtract the diameter of 2 moons from that, and that leaves us with this space right here, okay? If we compare the diameter or the radius of the Earth to that ratio right there, guess what the relationship is between those two numbers? It is the same as the surface area of Venus compared to the surface area of Earth. The ratio between those two distances is the same as the ratio of the surface area of these two planets, to an accuracy of 98.996%. Well, there's our second time, so that's just coincidence, all right? So let's go beyond happenstance, let's go beyond coincidence. Let's take the diameter of the Earth compared to the diameter of the Earth plus the Moon, and it equals the golden ratio to 99.92%. If you took the diameter of the Earth and you compare it to the diameter of the planet Mercury, that's a much bigger distance, but that is the golden ratio squared to an accuracy of 99.86%. If you take and start with the planet Earth and you draw a pentagon outside of its diameter, okay, so we'll put a pentagon outside of that, and you see how the edge of the Earth is barely touching the edges of the pentagon. Now we're going to draw 5 circles whose diameter connects to each of those 5 corners. So we're going to put 5 circles around there, and they connect to all 5 of the circles on this pentagon. Now you have a space that's left inside of those circles, okay? So we're going to put a little circle inside that yellow circle. That yellow circle equals the diameter of our moon to an accuracy of 99.99%. Okay, now we're moving past coincidence, all right? Let's start with the planet Earth and draw a pentagon inside of its diameter. The distance between any 2 non-adjacent points on this pentagon, we'll represent by these 2 lines here, equals the diameter of the planet Venus to an accuracy of 99.90%. It's as if God is using the planets as a ruler or a yardstick to say, here's how I'm going to lay out everything in the solar system here, just so you can discover it later, and just so you can say, coincidence? I think not. How about this? Let's start with the planet Earth. We'll draw a pentagon inside of that, and then we'll draw another pentagon inside of that, and then we'll draw another one inside of that. Then we'll draw a circle inside of that pentagon, and that represents the diameter of the planet Mars to an accuracy of 99.40%. Let's start with the planet Earth. We'll draw a pentagon inside of its diameter, and then we'll draw a pentagram inside of that. We'll draw a circle around that on those, touching those 5 points. Diameter of Mercury to 99.86%. Now, Nicholas Copernicus was a famous astronomer from years back, and he said this: the mechanism of the universe wrought for us by a supremely good and orderly creator, the system, the best and most orderly artist of all, framed for our sake. Our sake in what way? So that we could discover these things and we could give praise to God who put them there in the first place. God is amazing. God knows his math, and he has displayed some of that in his creation. I want to take us now to this aspect of the Mandelbrot set. So this is the man here. His name was Benoit Mandelbrot. He was born in Poland in 1924 of French and American ancestry. He became in his adult life a mathematician at the IBM Thomas J. Watson Research Center, and he is actually the one who coined the term fractals for those patterns that we saw earlier. Now, I introduced you to the set of Mandelbrot numbers, right, using this formula. And so we're going to run some of these, and we're going to look really quickly at what are these numbers that belong to the Mandelbrot set, okay? Now, he did this in the early 70s, before there were computers that could calculate these things, so it could be plotted out by hand. But let's just start with, we're asked the question, is the number 1 part of this Mandelbrot set? So we'll start with c equals 1. We'll plug in the expression zn squared plus 1, and so we have 0 squared. We start with 0. You always start with 0. 0 squared plus a 1, and we get the number 1, so we plug it in there. And we drop it down, and we get it there, and we say, okay, and then what happens is we put 1 up in its place, and 1 squared plus 1 equals 2, so we'll move the 2 down there. Whoa, went a little too fast. Hang on. Didn't mean to hit that button. Okay, 5 squared plus 1 is 26, so we bring 26 down, and then 26 goes up, and 26 squared plus 1 equals 677. You get the idea. So does the number stay small? No, it does not stay small. We can see that this number here, so 1, we can say is not part of the Mandelbrot set because the number did not stay in the small realm. So we can say, no, the number 1 is not part of the Mandelbrot set because it does not stay small, so we'll take number 1 and we'll put an X to it. 1 does not belong. Let's look at 0. Well, we know that if we take 0 squared, it's going to get 0. We're going to add 0 to that. We're going to get 0. And we're just going to get a repeating 0. So we can say, yes, the number 0 is part of the Mandelbrot set because the numbers there stay small. So for by 0, we're going to put a little check mark by that. Let's look at the number -1. What happens if we put -1 in its place? Well, we see 0 squared plus a -1 equals a -1, okay? And we put -1 in there, and then we multiply that, we're going to get -1, 0, -1, 0, repeating again. So we would say, yes, for -1. -1 is part of the Mandelbrot set because the number stays small. And so we'll put a check by that. So, now, we've all worked with number lines before, right? We've understand how this thing works. We have the number line. We start with 0. Everything on one side is positive. Everything on the other side is negative. Okay. Well, now we have to get a little bit ugly with numbers. Well, ugly isn't the best term. We got a little more complicated here, okay? Because we need to talk about something called imaginary numbers. Now, we already said that numbers are conceptual anyway, right? Now, we were all taught in school that when you multiply, when you square a number, okay, a positive number, positive times positive is positive. If you square a negative number, negative times negative is positive, okay? And if you take a positive times negative, okay, well, in imaginary numbers are defined as a number that when you square it, when you multiply it by itself, you get a negative number. Okay, now, for the purposes of basic math and high school math, basic algebra, okay, that applies. But imaginary numbers do exist in reality. There is conceptually, because numbers are conceptual, conceptually you can have a number that when you multiply it by itself, the answer is a negative number. Now, just to throw in more confusion, all the other numbers who aren't imaginary numbers are called real numbers. Okay, but they're all numbers, and they all have this property of being conceptual. So, just kind of clear that away. So just temporarily, if you're confused by that, just kind of park that aside and say, I was always told that, okay. But you can have a number that when you multiply it by itself becomes a negative number. So look at the Mandelbrot set. So you have these numbers here, and really I'm kind of moving quickly through some of this. I understand, but it's worth it if you hang on. So just looking quickly, 1 we said is not, but 0 is, and -1 is, and -2 is, but -3 is not, and 1/2 is not, but 1/4 is. And looking at some of these imaginary numbers, I is, -I is, 2I is, -2I, or -2 is not, and 2 is not, but 1/2 I and -1/2 I are. So it's like, okay, where are we going with all this? All right, back to our number line here, okay? So we know how number lines work in this direction. So now we're going to create another axis where we're going to have these imaginary numbers so we can go off of this line and we can plot this in a two-dimensional way, okay? So we can plot numbers anywhere off this, even to use the term off axis, which means off of our x-axis. When we plot the Mandelbrot set, okay, now remember, when Mr. Mandelbrot came up with these, discovered that there were some numbers that stay in this set and not, he set out and they took and make graph paper and they started plotting what numbers could fit inside of here. But you could only get so much detail. In the 1980s, when the computers had enough computing power, they could start plugging in and having the computer display it graphically. And when they did, this is what came up. And just to make it easier, we'll take away the number lines there. Okay, so this shape, this main shape is called a cardioid, and you have spikes and circles and various other things going on. Now, the one thing you do know, remember about decimals, is that you can always plug in a 0 and keep moving a number, and you can have it 0.01, 0.001, 0.00001. You can keep doing this kind of thing. So you can keep making numbers infinitely smaller. And what we're going to do is we're going to look at the Mandelbrot set this way. Now I'm going to escape out of this PowerPoint, and I'm going to pull up a Mandelbrot program because I don't have the ability to integrate that. And I have to, hang on a second here. I'm going to move this over. And I'm going to stretch it out if I can find my cursor here. Come on, baby, get on there. All right. Now, I have to, because I'm not duplicating, I have to get over here where I can see this a little bit. All right, now I move my cursor back up here. And we're going to go look right up here at the top a little bit. And we're going to click that square, and we're going to magnify this. Now, I want you to see how there's like this first big circular blob coming off the top. Going up from there is another small circular blob coming off that. And then you see these spikes coming out. And this one has 3. It goes 1 going up and 2 going out this way. So you have 3 little spikes. And then this one you see here goes up, and it has 1, 2, 3, 4, 5 little spikes. 3, 5, these numbers start to look familiar. This one in the middle, what do you think it's doing? Well, if I took the number 3 and the number 5, add them together, you get the number 8. So if I zoom down over here, and I say, let's enlarge that and take a look at it. Well, what do you know? There just happened to be, let me get that mouse cursor off of there. There just happens to be 1, 2, 3, 4, 5, 6, 7, 8 spikes coming off of this number. So this little thing is adding little numbers as it goes. And if this is 5 and this is 8, this one has 13 little numbers coming off. And this one has more. And so these numbers, as we keep going in, and we can look at these just for fun, click, magnify, and we see these patterns. And depending on how much computing power you have, depends on what you're looking at. Let me scoot over here a little ways and go back to this one. Now, the colors are being assigned by the computer based on the number of iterations it takes to drive out of the Mandelbrot set, because it may take several applications of that formula before the number finally exceeds the number 2, which is the threshold for this. So if it's in the set, it stays black. But if it's out of the set, but it took several different runs of the formula, then it depends on what the color is. But so the computer did not create these colors, but the patterns that you're seeing are created by the number set itself. Now here's the point, because we're going to look at this a little bit more. Before Mr. Mandelbrot ever discovered this set of numbers, God, in his mind's eye, if you use that expression, knew what this pattern would look like. He knew that someday mankind would discover this pattern, and he made it beautiful and amazing, artistic. But watch, if I go up here, and again, I've got to be able to see where is my cursor. Up here. I'm going to go over here. I'm going to go to my color bar, and I'm going to set it on monochrome, just to show you that the colors are immaterial. You still have these incredible patterns. All right, let's back out. Now we'll go back to the home page here. And we'll go to this little valley right between here. Oh, and we'll go in and we'll just keep zooming in there. And we'll see the same kind of things happening. And I want to go back to the color patterns because it just helps, it makes it a little bit easier for us to see. And I'd like number 4 myself here. Just 1, 2, 3. I think this is it right there. And what do you notice appearing in that little spike right there? Well, let's go down and take a closer look at this thing and see, what is this little blob? We have a baby Mandelbrot. The pattern is repeating again. And if we come off this little baby Mandelbrot and follow it out, we're going to find, what do you think we're going to find? Another and another. And as long as we have the computing power to look at it, we can keep zooming in and we can keep finding all kinds of amazing patterns. Now, if I keep doing this, the computer eventually is going to say, hey, you're wearing me out here. So I'm not going to spend too much more time on that because I see the clock is not acting in our favor right now. But if we go over here and look in these areas here, in these valleys, you see, and again, we can zoom here until we run out of space. But it wasn't until computers could run these kind of computations that we could see this. But you see, we have over here, we have little swirls that look like seahorses, and over here we have a double spiral. This arm comes in this way, this one comes out this way, and if we keep circling on that, we can just keep going and going and going and going and going and seeing more and more patterns and more diffusions going on. And here we have little Mandelbrots again reappearing. So my point again is this. Man did not invent these patterns. God built these patterns into mathematics for mankind to come along later and discover and to say, there's beauty, there's complexity, there's organization. That sounds like the mind of an intelligent creator. It doesn't sound like these could have come about randomly. These aren't random patterns, they're organized patterns. But people who want to believe in the Big Bang have to believe, yeah, it all just got here randomly. Well, this right here is a way, oh, and by the way, let me tell you something here. I think this will shrink it back down. Yes, all right, we're good. Now, back to PowerPoint. And I have a picture of it, but I never got around to actually. If you have an Android phone, you can go to the Google Play Store, type in Mandelbrot, And you'll get several different free Mandelbrot apps that you can load on your phone, and you can do the same thing on your phone. And I believe Apple probably has it as well, but I don't have Apple, so I can't verify that's on the Apple Store. So I don't have the power on this computer to take you very far into the Mandelbrot set. But somebody with a computer that did, and they created a movie, and we're going to just follow this for a little while. It's just going to zoom in. And I want you to just sit back and be thinking that God, in his mind, as he's laying out creation, he is able to see what you're seeing now before any human being ever was able to do this, before any computer could ever take us this far. If we can look at flowers blooming in our gardens and find beauty. Oh, what's this coming up? Oh, there's baby Mandelbrot again. If we can look at flowers like lilies or daisies or daffodils and find beauty and complexity, how much more can we find it here in these wonderful patterns? And again, because these are conceptual in nature as a fractal, this, in theory, could never stop. You'll run out of computing power before you ever get far enough into this. But having taken all that computing power and put it into a movie format, we can watch it for a little while. And again, the patterns are determined based upon the number of times it took to run the equation to determine whether the number stayed in or left the Mandelbrot set. Now, in trying to find a way to summarize all this, I was like, well, I could talk about this, talk about this, talk about this. And I thought, maybe there's somebody out there who can say it as well or better than I can. And I think I found somebody who did a pretty good job. This is available on YouTube. If you go to YouTube and type in God and Mathematics, you can find this video. You can watch it again yourself. I'm going to play it. It's just about 5 minutes long. So sit back and enjoy what they have to say, and then we'll be wrapping up.
Why does mathematics work? Think about it. Mathematical entities like numbers, sets, and equations are non-physical and abstract. They can't cause anything. Yet, for some reason, the physical universe operates mathematically. As Galileo put it, the book of nature is written in the language of mathematics. Scientists do not use mathematics merely as a convenient way of organizing the data. They believe that mathematical relationships reflect real aspects of the physical world. Science relies on the assumption that we live in an ordered universe that is subject to precise mathematical laws. Thus, the laws of physics are all expressed as mathematical equations. For example, Pythagoras discovered that when a vibrating string is shortened by half, it plays the same note 1 octave higher. Isaac Newton's observations led to his discovery of the law of gravity, a mathematical relationship expressed as a simple equation that enabled us to enter the space age. Mathematics enabled astronomers to pinpoint the location of a previously undiscovered planet, and James Clerk Maxwell used mathematics to predict the existence of radio waves. Albert Einstein, working with theoretical mathematics developed 50 years earlier, formulated his general theory of relativity, a pillar of modern physics. His calculations were later confirmed during the solar eclipse, when Arthur Eddington observed light from distant stars bending around the sun. Then, Peter Higgs used mathematical equations to predict the existence of an elementary particle. It took 48 years, billions of dollars, and millions of man-hours for experimental scientists to finally detect the Higgs boson. How do we explain the astonishing applicability of math to the physical world? In 1960, the Nobel Prize-winning physicist and mathematician Eugene Wigner published an article that stunned the scientific community entitled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." Wigner concluded that the effectiveness of mathematics is a miracle. which we neither understand nor deserve. Why is mathematics so effective? Philosophers who address this question fall into two camps. Naturalists, who believe that all that exists concretely is space-time and its physical contents. They exclude supernatural causes. And theists, who believe in a God who created the universe. Naturalists cannot provide a reasonable explanation for why mathematics applies to the physical world. It's just a happy coincidence. But this is no explanation at all. At most, naturalists can say that it's not surprising that math applies to the world, because the world itself just happens to have a mathematical structure, so of course mathematics applies to it. But this explanation is unsatisfactory for two reasons. First, a great deal of mathematics in science cannot be physically realized. For example, imaginary numbers and infinite dimensional spaces. Although these concepts are useful, physical reality cannot possibly have the structure they describe. And second, this answer still doesn't explain why the physical universe has such a stunningly elegant mathematical structure. By contrast, for theists, mathematics works so well in the physical world because God has chosen to create the world according to the plan he had in mind. The first-century Jewish philosopher Philo of Alexandria offered this analogy. When a king wants to build a city, a trained architect first designs in his mind a plan of all the parts of the city that are to be completed. Then he begins to construct the city out of stones and timber, looking at the model and ensuring that the material objects are built according to the plan. Mathematics and physics work so well together because the same mind that designed the universe on a mathematical model also built the universe on the same mathematical model. All of this adds up to an argument for the existence of God that goes like this. If God does not exist, the applicability of mathematics is just a happy coincidence. But the applicability of mathematics is not just a happy coincidence. Therefore, God exists. Eugene Wigner was right. The effectiveness of mathematics in the physical world is quite literally a miracle, which is best explained by the existence of God.
YouTube, God and Mathematics, you can find it, you can watch it as many times as you want to. Psalm 19, verses 1 and 2 tells us, well, before we go there, reminder, God and numbers are non-material, they don't reside in physical space, and they have always been the same. Psalm 91 and 2 tells us, the heavens declare the glory of God, and the firmament shows his handiwork. Day unto day utters speech, and night unto night reveals knowledge. Psalm 40, verse 5 says, many, O Lord, my God, are the wonders which you have done, and your thoughts toward us. There is none to compare with you. If I would declare and speak of them, they would be too numerous to count. Psalm 90, verse 12 tells us, so teach us to number our days, that we may present to you a heart of wisdom. Psalm 139, 17 and 18. How precious also are your thoughts to me, O God. How vast is the sum of them. If I should count them, they would outnumber the sand. When I awake, I'm still with you. I like Psalm 8, which starts off, O Lord, our Lord, how majestic is your name in all the earth. You who have displayed your splendor above the heavens. When I consider your heavens, the work of your fingers, the moon and the stars which you have set in place, what is man that you think of him? And a son of man that you are concerned about him. Psalm 19, verse 160 tells us, thy word is true from the beginning, and every one of thy righteous judgments endureth forever. In the beginning, that would be Genesis 1:1. When God created time, in the beginning, God created the heavens, space, and the earth, matter. And everything else in creation as well, including numbers. Now, I want to reiterate, this is a Sabbath morning, that the cross, the crucifixion event, was the most significant event that took place on the planet Earth. The most significant geological event was creation, of course, but John, in the book of John, Jesus is saying, and when I am lifted up from the earth, I will draw everyone to myself. the same God who died as our Savior is also our Creator, the one who invented everything and brought everything into existence, including mathematics. Our God is holy. Our God is majestic. Our God is awesome in power and wisdom, and He is deserving of our praise. And so do we want to have the closing song, then the benediction, or the benediction and then the closing song? And how do you want to do it, Diane? Benediction first. Okay. And then when Diane comes up, she's going to tell you a little bit about something that we have planned for later on this afternoon, kind of an impromptu thing. So if you'll bow your heads with me, please. Lord God, we're surrounded by mathematics all the time, so much so that we don't even give much thought to what they say about you. But today, we've had our eyes open a little bit more, and we're amazed at how you put everything together based on what you had in your mind. And you've given us a little glimpse into that today. And I pray that we will all take that and build upon that. And as we go from here, that we will have more assurance and more confidence that you know what you're doing, you're in control, and you've told us that you're on our side and that you are looking out for our best interests and that you're going to get us through all the difficult days ahead of us. But as we see these difficult days approaching, we also know that that means that our Savior Jesus' coming is even closer than before. And so we thank you for all of that, and we thank you for the assurance that we have today that your word is true and that you love us. And because you love us, you would never lie to us, and you've given all this to reassure us of our relationship to you. And we thank you for all of these things and the time that we spent this morning in this sanctuary. In the name of Jesus, amen.